Good morning. I'm going to talk to you today, and Ken from Wood Environment and Infrastructure will be joining me also to talk to you about our NCDOT Bridge Superstructure Level 3 Wave Vulnerability Study Report and GIS Database. This impressive image from NOAA depicts the paths of all major hurricanes and tropical storms affecting the U.S. over the last 170 years. And this shows all of the named hurricanes that have hit the U.S. East and Gulf Coast in the past 67 years, and over 20 have hit the North Carolina coastline. From this graphic, we can see that North Carolina experiences major hurricane events on about a 5 to 7 year return interval, similar to the southern tip of Florida. So in 2004 and 2005, Hurricanes Ivan and Rita significantly damaged critical bridges in the Gulf Coast states. Federal Highways initiated a pooled fund contract, which resulted in the development of the AASHTO guide specifications for bridges vulnerable to coastal storms. 10 states were involved in this pooled fund study. The AASHTO guide was published in 2008. Ocean Engineering Associates was on the research team, and NCDOT contracted with Ocean Engineering Associates in 2010 to study its coastal bridges for vulnerability to storm surge and wave loading. So the NCDOT report was published in 2013. 191 bridges were examined out of 222 considered. 105 bridges were determined to be vulnerable. Vulnerable meaning that if the surge and wave forces and moments exceeded the resistive forces and moments by the dead weight of the superstructure for any span, the bridge is considered vulnerable. So 58 of these were selected for being analyzed in detail. And this study is based on a level 3 analysis of 62 Hindcasted storms from 1850 to 2010. A level 3 analysis requires extensive computer modeling and analysis effort that should be performed by a qualified coastal engineer. In 2015, we also contracted to add the 5, 10, 25, and 50-year return interval data. The study results were produced in the report and also in a GIS database because it was a massive amount of data that was too much to just put in a printed report. For the 58 detailed bridges that were studied, this is a sample of some of the the detailed output for the selected bridges, and it also included for each of those a profile which showed the low chord of the bridge, the 100-year water surface elevation, the 100-year wave crest elevation, and the bed profile. For the storm surge and wave modeling, the wind and atmospheric pressure fields data was provided by Ocean Weather Incorporated. The ADCIRC model, Advanced Circulation Model for Ocean Hydrodynamics, simulated tidal circulation and storm surges. The SWAN model, simulating waves near shore, simulated wave heights and periods. A finite element mesh of over 207,000 nodes was developed. And this is a view. This finite element mesh was developed using topography and bathymetry interpolated from NOAA data sets covering the Atlantic Ocean, the Gulf of Mexico, and the Caribbean Sea. And this is a close-up of the mesh along the North Carolina coastline. For model calibration, an iterative process was used to match measured values within acceptable limits. The 3 types of measured data that were used for calibration were the water surface elevation data, hurricane high water marks, and wave data. So for model calibration, 2 types of observed data were used at 4 NOAA gauges. One was a time series water surface elevation during a normal month of tides with and without meteorological influences, and 2 4-time series water surface elevation data associated with 4 hurricanes, Fran, Bonnie, Floyd, and Isabel. For the SWAN calibration, they used 4 National Data Buoy Center wave stations, and the average error was plus 10%, ranging from about 5% to 23%. The Hindcast procedure that was used employs the tightly coupled ADCIRC and SWAN model. And since the models share an identical mesh, they pass wind speeds, water levels, currents, and radiation stresses efficiently, allowing them to run sequentially in time. The study examined all the historical tropical storms and hurricanes occurring within 100 miles of the North Carolina coastline. 62 storms were selected for a 160-year record. For additional data, the storm paths were shifted half a degree left and right, approximately 30 nautical miles of the actual path for 124 additional simulations, which is a total of 186 for the extreme value analyses, giving an effective 480-year record of data. So this is a graphic of the paths of the storms and a listing of the 62 storms that were studied. For the extreme value analyses, design loads for the structures were based on the probability of exceedance, and AASHTO recommends using a 1% probability or the 100-year return interval. The cumulative distribution function method was used for estimating these 1% values. A bootstrapping method was employed to examine the effect of the astronomical tide phase, and the details of that are in Appendix E of the report, which is on our website, and we'll give you that link at the end of the presentation. So with the availability of 480 years of historical data, the 100-year return interval data for all the parameters of interest were calculated using that cumulative distribution function method. So the extreme value analysis results produce 2 sets of data. One is the maximum 100-year water surface elevation and associated wave height, and 2, the maximum wave height and associated water surface elevation. The data needed as inputs to compute design wave forces, or this data was needed to compute the design wave forces and moments for the subject bridges. For the surge wave loading and bridge vulnerability assessment, a physics-based model proprietary program by OEA was used to compute the vertical and, I'm sorry, didn't push the slide forward. A proprietary model by OEA was used to compute the vertical and horizontal forces and moments, and based on predictive equations by Dr. Max Shepard and the graduate students at the University of Florida. So the results were 105 bridges were considered to be vulnerable to the 100-year surge wave loading. NCDOT requested detailed analysis on 58 of these. Detailed results were presented in the final report and the accompanying GIS report. So this shows the 58 bridges that were selected for detailed analysis. And this database includes the depth average current speed, current direction, wind speed, water surface elevation, wave crest elevation, significant wave height, and maximum values for the 62 storms. So these are just some screenshots from the GIS database. This is the 100-year water surface elevation, the depth average current speed, the 100-year current direction, wave crest elevation, significant wave height, and then also various online and offline base maps, vector USGS quads, NAIP, and other aerial imagery were provided in the GIS package. How has NCDOT been utilizing this? Well, we've been using it to provide design data for our coastal bridges and our hydraulic design reports, such as the water surface elevation for reported return intervals. And our structures management unit uses this data for analyzing existing bridges and locations for new bridges. And then design parameters such as flow velocity and water depth from the level 3 study can be used to calculate tidal bridge scour up to the 100-year return interval. For very long bridges, data may be needed at each span location, so the hydraulic staff provides tabular data upon request, similar to that's shown in the next slide. And as you may imagine, it can be a very tedious effort to populate these tables by a manual point-and-click procedure. And so next, I have Ken Ashe, who's going to share with you what his firm has been helping us with to discuss what we're doing to make this data publicly and more efficiently available. Ken?
So I get to be the first guy that chooses not to have a pocket on my shirt with a lapel microphone. So give me 1 second. Our part in this has been a relatively a small part. There's great data, and going back to what Jerry said, it's really cool that you can look and see that only 1 or 2 or 3 of these piers are at danger from wave action, on the far left side there. But you have to know which pier you're looking at, and you have to go to the table and pull the data out. The nomograph's a great idea, but it ends up meaning you have to go from knowing where you are to a piece of paper and then back and forth. And to reinforce what Jerry showed, you've got a couple hundred bridges. Some of these have data, and I put this GIS image back up because when they asked me to come in and look at it, they were saying that it was a great platform, it had worked really well, but it was getting a little bit bulky, it was a little bit of an older technology, and just pointing and clicking to pull information out of it was taking 4, 5, 6 minutes or even longer to get the query to come out. And as Jerry's saying, if you're pulling data from a long bridge, 20, 40 or more spans, you multiply that by 4 or 5 plus minutes, it's taken a lot of Jerry's time. And so I didn't really believe that. We took the data back to our shop, and it actually was slower at our shop. So assuming that DOT had bad infrastructure and communication rates internally in their server was a bad assumption. It was just something the way with the database was put together. And it's just a query. You know how GIS works. You couple that with, there's 2 pieces of information. There's the hard copy report or the PDF report that has the physics-based model, and you've got the GIS data for the wave data in a different place. You have to look in 2 different places, and it's cool. The back of the report has a lot of good information. This one's color-coded green because the waves actually don't affect the low chord of the bridge, but there's a vulnerability index, whether the bridge is at danger, and there's they note whether the bridge is important for economic purposes or emergency evacuation routes and things like that. And then everything from the physics-based model is stored in that. So the original study contractors did a great job providing a lot of information. So we had 2 tasks. One is try to make it a little easier and quicker to use, and 2, try to get it to more users as a base, at least the consultants in the consultant pool that works for DOT. The question about serving to the public is kind of an unresolved issue. It's not sure that the public would understand it in the first place. So first thing we thought was, let's put it all in a database, let's put it in a geospatial database, and let's serve it out on something that looks like AGOL. So we were tasked to do some piloting to make sure that that would work, to show that it would work quicker. And this is just snapshots showing that what you know from AGOL, if you've used it already, is that you can change from legend to contents. And this gives a hint of some of the data we've got stored, and you can change the background. So we set up a database structure. And first thing we thought is that a lot of the work they've been doing already is just working on existing bridges, answering questions about existing bridges. So we just decided to bulk populate the bridges themselves with this data. So we had to go in and digitize each of the bridges. That's just a small GIS task. And if you look, the devil's in the details. There's an east and westbound set of lanes here. That's important because in the study, The westbound lane is considered a bridge, which has its own physics-based model, and then the eastbound has its own model. One of the things we did is we went ahead and took from the original PDF the actual sheets for each bridge for the physics-based model and made those linkable, where it's the PDF link there. You can actually grab that if you want to print it or have it instead of going back to the original report. So it's at hand. You click the bridge, you click the report, and it's there. We also, on the where it says show related tables, that's where the depth of data has been put in one spot. This is an early version. We've actually gone through a couple of revisions, and there's another little piece of the story at the end. But all the water surface elevation data, we went ahead and did a bulk geospatial analysis to query each of the bridges to pull the data in. And that's just visible in attribute tables down at the bottom. The functionality of AGUL allows you to pull that out. It's one of the things that's one of the next steps for DOT is to make sure that it can be pulled out in a reporting the way they need, or in an Excel spreadsheet or a text file. We went a little further and made sure that since the physics-based model was done by the span, and some of the bridges in the state, depending on where you are on these longer spans, the data may be different from one end to another depending on the bathymetry, the assault angle of the storm. So we digitized each of the spans. We made those match the physics-based model. The span links were in there. We did a little bit of heads-up digitizing to make sure those matched visible piers or shadows from the bents. We did have a few bridges where the math didn't work, so we did some fuzzy math with Jerry's permission, of course. Some piers were over ground. Things didn't seem to make sense. But what that allows you to do when you run the GIS data is you can click the span and all the information is available there. The wave height information, the velocity information, including the data from the physics-based model. You can drop down and pull. You can see and link, and whether you want 50-year or 10-year, whichever it is, the data's there. And I mentioned that this is an early version. There's still some roughness in the attribute fields and the way the data is stored. So Jerry, we're cycling back again. So that's it for the content. The next steps are, once it's in a database, it allows it to be a bit more useful. We've been talking with the Department of Information Technology. Unfortunately, in the state of North Carolina, the legislature has mandated that if you want to put out a website or build an application, the DIT has to do it. So we've met with them to show them that this is actually servable on the web. It's point and click, it's fast, instead of the way it was slow in the past. So there's a requirements analysis documents being put in place to figure out whether it'll be served on AGUL, a web portal, or some other platform they choose to do. The next piece is DOT also wants to make sure that they can get information from the wave study, from the ADCIRC study on non-bridge locations. And we've suggested to the DITs that you rasterize it and use an image service to push it out. They're looking at some newer, cooler ideas like vectorizing the rasters or some other solution, but that's also something that has to be figured out. But beyond that, you can now color code, changing the legend and the schema in the web platform to show which sections or which bridges are vulnerable. That's important if there's going to be maintenance on a section of a bridge, that they need to go ahead and think about anchoring it against the assault of waves. Is it something that's going to overtop? The state assistant hydraulics engineer, Matt Laufer, has suggested that we mine that data with the LIDAR and the bathymetry data that the state has to go ahead and do some bulk scour calculations, just global, put that in the database and make that available. So that in addition to having the depth and the velocity there, you take it to the next step and give an idea of what the scour might look like. Because for some of these bridges, it's really critical. I think at Oregon Inlet, the scour depths can get minus 70 feet. And then lastly, DOT works really closely with emergency management. Emergency management does a lot of stuff real time during a storm using the HRVAC, the Hurricane Center data, to rasterize and map it quickly. This data can be coupled to show during the storm, is the deck at danger of being overtopped? Is the deck in danger of experiencing the wave action that would cause some of the vulnerability shown in the study? So with that, questions?
Did you, I may have missed it, but was sea level rise an assumption made here that you could recall?
No, that was one note I meant to mention, is that sea level rise was not considered something that we wanted to evaluate with that study, and that may be something if we go back and try to do some updates to the study. We were thinking about adding sea level rise considerations, and also we don't have the 500-year return interval. We'd probably like to add that. And I think also just there were some other things that we might look at, like storms since 2010 that have affected the coast. We'd probably like to add those too.